Hello, my name is Yeardley, and I am a PhD student for the Department of Chemical and Biological Engineering at the University of Sheffield. I work within Dr. Solomon Brown's research group closely with Dr. Robert Milton. And during this specific piece of work, I collaborated with Dr. Peyman Moghadam. I used my machine learning work to aid in the development and scientific research of metal organic frameworks for gaseous storage. As an introduction, metal organic frameworks, often abbreviated to MOFs, are a unique class of crystalline porous polymers, which excite scientists due to their flexible nature that allows the design of pore structure and functionality. The self-assembly process involves bridging metal building units using organic ligands as shown in this image. This flexible nature has enabled a very large number of MOFs to be synthesized, specifically around 88,000. This is great, but it does cause difficulties in identifying the top materials for each specific purpose. This research specifically focuses on aiding the identification of suitable synthesized MOFs for gas storage. To do this, we have used machine learning techniques, and literature has already proven that machine learning provides the perfect technique to help screen new MOFs and predict the gas uptake capacities. As machine learning is a popular technique used for MOFs, it is important I make the novelty in this work clear, and so here I shall highlight my objectives. Specifically, this work will use machine learning to investigate the effect of the geometric properties of MOFs for gas storage application, applying a quantitative sensitivity analysis for the first time to determine which are the most dominant properties. Then, we shall further the investigation by asking, how do such properties change across different scenarios, such as different storage pressures, and in particular across different gases. Finally, this work's main objective is to use a novel reduced order modeling technique based on Gaussian processes to predict the deliverable capacity of synthesized MOFs, irrespective to the nature of the storage gas. To do this, the mathematical background involves the use of Gaussian processes, often which I abbreviate to GPs, as a machine learning technique that takes training data to optimize hyperparameters in this equation. This is done using standard Bayesian condition. Essentially, the GP becomes a black box function that can predict the deliverable capacity of MOFs given the geometric properties as input variables. So, the GP takes a 1/d row vector of input variables x, returning a Gaussian random variable as an output. It predicts the mean and the standard deviation, giving a level of uncertainty in the predictions. The learning is done to optimize a similarity function, which expresses the correlation between the responses to the input variables. This work optimizes the hyperparameters using the ROM software library freely available on GitHub. As mentioned in the objectives, this work hopes to quantify the effect of the geometric properties on synthesized MOFs for the first time. In previous literature, to my knowledge, the properties have been investigated, calculating the ARD length scale of hypothetical MOFs. However, these length scales do not give a true quantitative value for the impact, and instead show more of a qualitative rough estimate to the influence each geometric property has on the deliverable capacity. In this work, we use symbolic indices, a variance-based global sensitivity analysis, which decomposes the variance of the output into terms that are dependent on the input variables, shown in the following equation. The GP gives a black box function, where the mean is used to analytically calculate the symbolic indices. Finally, the novel reduced order modeling technique uses a combination of GPs and symbolic indices to optimize and reduce the input basis. This is done by combining and rotating the input by theta, so that the symbolic indices are optimized to maximize the primary dimension, then the secondary dimension, and so on. The calculations can be quite onerous, but overall are effective in reducing the model. So, a summary of the mathematical background. First, we use Gaussian processes, a machine learning method to turn a MOF database into a black box function. The GPs are always validated using 5-fold cross-validation. This ensures inaccuracies are not carried over to the GSA. However, in this presentation, the validation of the initial GP predictions will not be shown due to time constraints. So you'll just have to believe me and trust me that they are accurate enough to continue. Then, symbolic indices will be analytically calculated to determine which of the geometric properties are most dominant. Finally, both these techniques will be used to create a reduced order model to aid in the prediction of synthesized MOFs to gas storage. An ideal MOF structure would have a large deliverable capacity, which slightly depends on several geometric properties, including the largest cavity diameter, LCD, the volumetric surface area, AB, the gravimetric surface area, AG, the density, ρ, the void fraction, BF, and the heat of absorption at 5 bar, H5, relative to each storage gas. This research focuses on investigating the impact of these geometric properties. We decided that both gravimetric and volumetric surface area should be investigated, and so the density was not included in the analysis due to the dependency between these three input variables. These geometric properties are used as input variables to the GP model. In this work, we conducted the analysis on both gravimetric and volumetric deliverable capacities, giving a perspective from both sides. Further, you can see here that the deliverable capacities distribution varies depending on the storage pressure and the storage gas. And so this research aims to investigate whether the importance of the geometric properties varies depending on the MOF storage situation. The first sensitivity analysis was done using MOF storage storing oxygen at 4 different pressures. And including the gravimetric and volumetric deliverable capacity, this meant 8 GP models were created, validated, and used for 8 global sensitivity analyses. The GPs enabled analytic calculations of the split indices, providing both first-order indices and total indices. Here, the first-order indices show the impact from a single geometric property alone. And in these graphs, this is presented by the bars with a filled colour. Then, the remaining of the total indices are made up from the interactions with the other geometric properties. Hence, these interactions or cross effects are shown by the bars with a crossed colour. A key result is the lack of an impact that pressure has on the GSAs. It can be seen that for each geometric property, the Savoia value has a negligible difference as the storage pressure changes. It clearly shows the most significant geometric properties are unchanged at different pressures. Additionally, it is worth noting that this quantitative sensitivity analysis has found the most dominant geometric properties are in agreement to that found from a qualitative analysis found in literature. Again, a GSA was conducted for synthesized MOFs. This time we compared MOF storing oxygen at 30 bar to MOF storing methane at 30 bar. Once again, a GP model was created for each output, making 4 GPs in total. Each GP was cross-validated before the split indices were analytically calculated. Interestingly, a comparison between the split indices for the 2 gases show a lot of similarities, but also some distinct differences. First, we can see that the blue bars corresponding to methane has a much larger effect from the interactions between geometric properties. But when we remove the interactions and compare the first order values, we see that both storage gases are actually quite similar, except for the void fraction, which is quite significantly more dominant for the volumetric surface area when MOFs are storing oxygen in red compared to methane in blue. Up to now, this research has found some significant key findings. First, we have confirmed quantitatively that the deliverable capacity is dominated by the surface area and the void fraction, whereas the largest cavity diameter has a negligible impact. We have shown that the storage pressure does not affect the impact of each geometric property, whereas a change in storage gas from oxygen to methane causes the interactions to increase, but again has little impact on which geometric properties dominate the deliverable capacity. After the GSAs, we want to extend this further by attempting to produce a new prediction technique that can be reduced and extended to predict the deliverable capacity of MOFs irrelevant to the storage gas. So we trained a reduced order model that, as previously discussed, combines the split indices and Gaussian process techniques to rotate the input basis. The rotation of a primary dimension by theta linearly combines the geometric properties. Here we can see the equation for theta for the primary dimension of a ROM, predicting the volumetric deliverable capacity of MOFs storing oxygen. Specifically, this is a dimension that has worked extraordinarily well, as it ascribes almost 80% of the total variance. This means it would be reasonable to reduce this specific model to just one primary dimension. Please note, this Savoia chart differs from previous charts shown, as the y-axis presents the cumulative split indices. It has also been reordered to increase in relevant dimensions. beginning with the primary dimension, the next is the secondary dimensions. Therefore, U2 shows the value for both U1 and U2. U3 includes U1, U2, and U3, and so on, until the last dimension always corresponds to 100% of the total variance. And we can recognize that all four ROMs can be confidently reduced to at least 4 dimensions, as they all have a cumulative spoil index value of 0.9 or greater. But other than being able to reduce the MOF data into an efficient black box, you may be asking, so what? What else do these ROMs offer to aid the investigation and discovery of new MOFs? How about if I tell you this? These ROMs combine the geometric properties in dimensions of importance, and so I believe this could help predict the deliverable capacity irrespective to the storage gas. In this work, I began the first stage of testing this hypothesis, where I've used the ROMs to predict the deliverable capacity of MOFs storing the opposite gas to what is streaming. To ensure validity, rules are set to ensure the predictions are analysed fairly. First, we gather all the data for all 2,740 MOFs storing oxygen. So we have the input variables paired with the output variables, and this data has been standardised. It is vital that we ensure the mean and standard deviation of each input and output variable is safe for later use. Cross-validation is used for testing again, and so the data is split into 5 folds, and 4 is used for training the ROMs. In this example, we have trained the ROMs with MOFs storing oxygen. So now we test the ROMs using the deliverable capacity of MOFs storing methane. To do this, we still want to use the remaining fold. Therefore, we shall replace the heat of absorption at 5 bar for the oxygen column with that for methane. And again, standardise the values for the mean and standard deviation that was saved from training. Then, the ROM has all the input variables needed to predict predictions. Finally, the predicted deliverable capacities just need to be compared to the true values. In this work, I personally prefer to compare standardized values, and so I take the true deliverable capacity of each MOF storing methane at 30 bar and standardize these values using the mean and standard deviation saved from training. This procedure is then repeated for all folds so that every single MOF has its oxygen data used for training and then its methane data used for testing. Now the important bit, the results. This table shows the results from all the MOFs, and the column showing the storage gas shows the gas which the ROM is predicting on. Therefore, if the storage gas says oxygen, then it was trained using methane data and tested on oxygen data. Incredibly, the high correlation coefficient and low outliers for each of the 4 ROMs help show that these can be used irrelevant to the storage gas. The predictions for the gravimetric deliverable capacity tend to produce more accurate results, with less than 3% of the MOFs lying outside of 95% predicted distribution from GP, and a much lower maximum error. But the results for the volumetric deliverable capacity are still very much satisfactory. This will certainly need to be thoroughly tested in more detail with a robust hypothesis test. But as a start, the results are very promising for the development of synthesized MOFs. To summarise the research, I am confident and excited to say that the objectives set at the beginning have all been achieved. We have determined the most dominant geometric properties to be the surface area and the void fraction. We have investigated the impact that the storage pressure has on storage gas and the influential geometric properties. And finally, we have developed a prediction technique specific to the synthesized MOFs to be used irrelevant to the storage gas. Successful initial tests have shown this to be a very promising line of research to be conducted in the near future. Further investigation into testing the ROM hypothesis will be conducted on more storage gases. Thanks ever so much for listening, and I am very excited for the opportunity to meet and network with as many of you attending the AIChemE annual meeting as possible. So please ask any questions. Also, please watch out for my other presentations where I hope to show you more uses of GPs for chemical engineering. Thanks a lot.